In this lesson, we're going to take a look at how rocket designs evolved throughout the early 1900s. So you remember that the very early history of rockets goes back to ancient times, almost mythology with rockets and weapons. Well, all that kind of took a scientific twist in the 1800s when science fiction writers like Jules Verne, as well as scientists, started kind of conjecturing about what might actually be feasible with rocket technology, whether traveling to space could really be a possibility. And this really ignited the imagination of legitimate rocket scientists who started building rockets. Now, this was a controversial science, if you will, in the early 1900s. People kind of made fun of people who worked on moon rockets and things like that. It seemed like they were kind of on the fringes. But really, the grandfather of modern rocketry is Robert Goddard. He's the one who really demonstrated that this is truly feasible by building a rocket. And I want to show you what that rocket looked like because it's kind of hard to make sense out of. This is probably like the most famous picture you'd be accustomed to seeing of this rocket. This is Robert Goddard. He's out on his aunt's farm, I believe. And what he's using is a liquid-fueled rocket. Now, this is an important distinction. I think I mentioned before a solid rocket booster or a solid rocket, solid fuel rocket versus a liquid-fueled rocket. A solid rocket is what you think of with a firework. Their inside is like condensed powder. It's hard. You light it, and once it starts, there's no stopping it. You can't really control it. You can't turn up. You can't make it speed up or slow down. It just goes. And that's how fireworks worked for a really long time. And they've been around for a long time. They're powerful, but they're kind of dangerous. A liquid rocket actually is what mixes this propellant with the oxygen, and you can control it. You can control the rate that it burns at, which means you can control how much thrust it provides. Now, this is key to making something that's safe, to making something you can control, frankly. And so that's really the innovation that Robert Goddard brought along, was these liquid-fueled rockets. Now, if you look at this rocket, I look at this and I'm like, where's the rocket? Okay, I mean, I see all kinds of different things here, but where exactly is the rocket? And so here's a helpful drawing that kind of shows all the different pieces. And you'll see that the rocket motor is actually at the very top of this entire assembly. And that the frame is all this metal stuff, but then what is this thing down below? Okay, we've got various valves. This is like the fuel tank, right? It says the liquid oxygen tank. And so then the gas would actually run up to the rocket motor itself. So you got the tank way down underneath the actual engine where the explosion takes place. Now, you think of an engine in a car, you think of all these complex moving parts. So one of the things about rockets is comparatively they're really simple because the engine is basically just a chamber where this explosion is taking place, this controlled explosion. So Goddard had this initial success, but he also then went on to refine his model and make better and better rockets over time. So you'll see lots of other pictures that Goddard was involved with as he built more sophisticated liquid-propelled rockets. And in fact, he was involved with the space program really until the end of his life. You can see here he is an old man continuing to work on rockets. So in that sense, he's like the grandfather of modern rocketry. Now, a next sort of historical step that's worth highlighting is really in World War II. This is the first time that liquid-fueled rockets are used in warfare. At least I think it's the first time. But it's certainly one of the most important because Germany invested an enormous amount in developing what's called the V2 rocket. And this is, again, one of the most famous rockets you'll ever see, the V2. A big rocket, okay, and a really destructive rocket. Let's see if I can give you the scale here. Yeah, so here's a V2 on a launcher, and you see these people standing down here. So you get a sense of how big this thing is, right? And it was a missile. It was designed to deliver bombs. And it was used by Germany and launched at its enemies during World War II, including England, right, in London. And so there's the pop-up again. That pop-up, it's going to get me every time. Okay, so the V2 rocket, one of the reasons it was so important, it was so destructive, it was an innovation in rocket technology, but really because Germany had invested so much, they had a huge brain trust. They had so many people who were rocket scientists and really the best rocket scientists in the world. And so one of the reasons the V2 is so important is because when World War II ended, all of these rocket scientists then were being sort of claimed by different countries. And that was a battle that the United States won versus Russia. Basically Russia and the United States. I mean, those were the two countries who were like divvying up the intelligence of these rocket scientists from Germany. And essentially, there's kind of some interesting stories around it, but essentially the U.S. went in and took as many of these rocket scientists as they possibly could at the end of World War II and brought them to help the United States develop our own rocket program. One of the most famous scientists from there is Wernher von Braun, and he's often credited with the entire U.S. space program, right? Because he came in and he led the charge. But these were people who worked essentially for the Nazis. They were creating rockets to kill civilians. They were not doing good things. And the United States took those people and basically put them to work on our military and civilian space program. So there's some shadiness around all of this. So when we think about the peaceful purposes that we, of course, went to the moon and all that, there is an undercurrent that we're going to talk about more of too in the next lesson of war in all of this. So the V2, just to get a sense of how this structure was compared to Goddard's rocket, as an example, you'll see there's the two tanks, which takes up the bulk. You'll notice this trend. In most rockets, the fuel takes up most of the space, right? So you've got the two tanks, you've got various control systems up front, and then you have the rocket engine in the back. Okay, and I don't know if you've ever looked at these images of like a rocket engine. They're so beautiful. If you ever get a chance to go to NASA and just see what these things look like, they're absolutely incredible. Just like all the wires going around. I mean, they're pipes. Yeah, here you go. All these pipes that carry the fuel around. They're just massive, and they're amazing. They're really cool. They're really cool. Okay, now if we keep going along from the V2, past World War II, you get to sort of like where we started building rockets for the space race, which we're going to get into later. But I just want to show you a couple early examples. What? This pop-up, my color scheme. Crazy. Okay, so the first one I'll show you is the R7 rocket. Okay, this is a Russian rocket that was actually used to launch Sputnik. And you'll see it has a really unusual design with these it actually has like these 5 engines, right? One on each, 4 on the sides and 1 right down the middle. So this is the R7 rocket. And I wonder if there's a nice schematic here too of what this rocket looked like on the inside. Let's just check the R7 schematic. Well, there's a schematic. That's pretty obvious. If you just look at that, I mean, it kind of makes sense. It's all right there. I don't even feel like it needs any explanation. Now, I'm just looking to see where is the fuel. In most of these cases, what you'll see is that the entire body of the upper part of the rocket is what's holding the fuel. But anyway, pretty cool. I actually have I have one of these that I wanted to print out like a architect drawing of a rocket that I wanted to put up in my office. I haven't printed it out yet, but anyway, okay. So that was a tangent. On the U.S. side of things, though, of course, the rocket development was primarily focused on military purposes towards the end of World War II, and then those kind of rockets were repurposed for human space flight. And one of the examples you can see is the Atlas rocket. This was one of the most sophisticated rockets at the very start of the human space program here in the United States. And you can see, again, it's quite large, but it's ultimately building on the same structure that the V2 was based on, right? Quite something. Now, of course, the fun is with the Kerbal Space Program, you can actually build all of these rockets. I haven't, because you need to download all these fancy mods, but I can show you some examples. See, for example, here in KSP is the Goddard rocket. Here it is in flight. You can see the fuel tank down below and the rocket engine above. It's flying right along. You can see the V2. Someone built the V2 rocket in Kerbal Space Program. So there that goes, launched. And even the R7. Here you go, beautiful shot of Russia's R7 rocket with the moon in the background. So people having lots of fun with the Kerbal Space Program. So pretty cool to see how these rocket technologies have evolved over time. We're going to see more of that in the next lesson as we get to the really big rockets that sent people off to the moon. All right, we'll see you next time.